Hello. Thank you for taking the time to listen to my presentation. My name is Claire Holmes, and today I'm going to be discussing Google Earth Engine and how it can be used to support high-resolution spatiotemporal analyses. I'd like to acknowledge my co-authors and their affiliations, which are listed here. Assessing pesticide fate in the environment requires either assumptions or empirical information regarding the landscape in which pesticides are used and areas in the proximity of that landscape. Regulatory exposure scenarios have defined environmental factors which allow consistent and transparent use of these pesticides. To investigate this, spatially explicit exposure studies are used to incorporate locally relevant information on a specific environment. These studies are often quantitatively selected to be placed into a larger regional context for regulatory decision-making. As more and more tools and better data have become available, the effort and cost of these landscape-based studies has decreased. This presentation will introduce functionality in Google Earth Engine that increases efficiency and transparency in landscape characterization studies, while reducing time and effort needed to complete them. As a refresher, remote sensing is a process of detecting and monitoring the physical characteristics of an area. With what I will be discussing today, this refers to the landscape on the surface of the Earth. As the diagram on the top shows, radiation from the sun is reflected off the surface of the Earth and collected by a satellite, passing through the atmosphere both ways. The composition and texture of the surface is important, and as you can see in the bottom image, different surfaces will return varying amounts of radiation for different wavelengths. By analyzing the measured reflectance compared to reference information, we can determine what is on the Earth's surface. Today, access to large repositories of recent satellite data and modern image processing methods allow us to gain more information with less effort. This information can be used to support landscape-scale pesticide exposure assessments. In general terms, Google Earth Engine is a platform for analysis of geospatial data and visualization of results. Google's goal for this platform is to let scientists do science by providing readily available pre-processed satellite imagery and datasets. This means your time can be shifted from collecting and pre-processing images to doing the analysis you want to be doing. In addition, there's no software download requirements for Google Earth Engine, meaning it's something you can access from your web browser. With that being said, since the processing is done on Google Cloud infrastructure, you will need an internet connection to use this web-based code editor. Coding can be done in JavaScript or Python via an application programming interface, or API for short, and to code in your web browser, you will need to use JavaScript. Let's start with a tangible output that Earth Engine can provide: interactively computing land use land cover maps. There are three main stages to this, which I've broken down here. The first is reference data collection, which can be done using built-in clustering algorithms like k-means to generate unique groups of similar pixels within an area of interest. The image here is an example of this unsupervised classification. It tells you which pixels are alike, but doesn't necessarily tell you what they actually refer to on the ground. An alternative is to perform manual reference data collection by inspecting the image and selecting points or polygons that represent your desired classes. Manual collection is all done through an interactive geometry tool in Earth Engine. To perform a supervised classification, the next step is to apply one of the machine learning algorithms built into Earth Engine using that reference data. An Earth Engine technique that Fabian Lowe introduced me to involves classifying an image with 4 or 5 of these machine learning algorithms and assigning each pixel to the most agreed upon class. For example, if a pixel is classified as bare soil by 3 algorithms and urban buildup by the other 2, the resulting pixel would belong to the bare soil class. This may leverage the individual strengths of different algorithms while having to also adjust the weaknesses, as they are compensated for by other algorithms. Finally, when the output is generated, it can be used for analysis within Earth Engine or exported for use elsewhere. Analysis options are almost endless, as almost every environmental question we might study has a spatial or locational aspect to it. One of Earth Engine's cutting-edge features is its collection of machine learning capabilities. Machine learning involves a category of algorithms that are used to find patterns in large amounts of data, like the multidimensional pixel data in an image. These approaches differ from traditional approaches, which often have difficulty with situations outside rigid boundaries. Machine learning approaches try to emulate a more dynamic approach based on ingesting large datasets. There are a few options for supervised classification algorithms, and there are options to import more complex methods such as deep learning using TensorFlow. TensorFlow is an open source platform used to develop and train machine learning algorithms. As I touched on before, by performing a fusion of multiple machine learning algorithms, a more accurate land use land cover map can be created than by using just one algorithm alone. In addition, there are performance assessment functions by using a confusion matrix or a more traditional omission-commission error. So now we come to actually obtaining the images in order to work with them. According to the Google Earth Engine website, they provide over a petabyte of image data, including the entire Landsat catalog, which has over 40 years of imagery using a comparable sensor so that long-term trend analyses can be conducted, Sentinel-1 and 2, which provide radar and spectral imagery at a 3 to 5 day repeat interval, multiple MODIS datasets that are value-added image products generated by NASA, and in limited areas, high-resolution imagery down to a resolution as fine as 80 centimeters. Users can also upload their own imagery to incorporate into their analysis. In addition, there's other datasets such as surface temperature, climate, atmospheric, weather, terrain, land cover, and cropland. Some of these datasets are global, while others only cover specific areas. One way to extract information about the environment from an image is using vegetation indices. I've given an example here using the Normalized Difference Vegetation Index on 2 images. This index, abbreviated NDVI, is calculated from the difference between the near-infrared and red light reflected by vegetation due to chlorophyll content and plant cell structure. A higher value indicates healthy, growing vegetation, and lower values indicate senescing or no vegetation at all, which could be objects like water bodies, roads, or buildings. The NDVI function is built into Earth Engine. All it takes is one line of code to calculate it, and then another to display it on the map. Here, I applied the function to 2 images at the same location on 2 different dates, and then calculated the change in NDVI by subtracting the first from the second. Blue colors on the final image indicate that there is more healthy vegetation in the second image, and red means the amount of healthy vegetation decreased in the time period. If you want to use indices that aren't built in, it's easy to use Earth Engine to select bands, perform the required calculations, and make your own custom indices. Users could even share the functions they've created with other users. In fact, it's highly encouraged. That's how science works. You add to the knowledge base that others have generated. In addition to the datasets provided by Earth Engine, users can also upload custom data. This could be in the form of raster or vector data, and you can work with these data the same way you would with Earth Engine supplied data. Vector data can mean point, line, or polygon data, and there's an example of each on the images shown here. Also, any custom geometry that you create in Earth Engine can be exported as a shapefile and used in other platforms. As an example, if you had training points identified in Earth Engine for a land use land cover classification, you could then export those training points and use them in different software. The bottom image on this slide is an example of soil polygons in Earth Engine. Using sets of polygons like these and a vegetation index like NDVI mentioned earlier, you can examine differences in vegetation vigor across a landscape, or across time within a single polygon. This might be useful when wanting to track or relate observed changes in a field, for example heat stress or poor yield, with other factors, such as soil properties or slope. So what would charting look like? As an example, this is a chart representing the moisture stress index of a single field, which has been calculated using Sentinel-2 images over a period of about 2.5 years. Because every part of a field isn't always the same, we can capture the variation of vegetation health within each field and show how that varies over time. This is showing the mean, 10th, and 90th percentile moisture stress index values of all the pixels in a single field for each date when images are available. Charting can be applied to single polygons, groups of polygons, one image, or many images, so it's a very versatile tool. Your standard chart types like bar and scatter are available, as well as pie charts, area charts, and others. This range of chart types makes sure your needs are met when visualizing data. Another useful type of remotely sensed information that Earth Engine provides is Sentinel-1's radar imagery. Typical passive remote sensing systems can only operate during the day because the sun is the source of the wave energy and are commonly impeded by cloud cover or atmospheric haze. Active remote sensing systems emit their own energy signal, so they can operate both day and night, as well as in unfavorable weather conditions. These systems provide information on the texture and aspect of surfaces based on the time it takes energy to be emitted and then travel back to the satellite. As an example, you could determine when a maize field has been harvested by comparing the rough texture of the tops of the maize plants to the relatively smooth soil texture after the harvest. In this way, radar data provide their own dimension of data and can be used to help fill in the information gaps when conditions for passive remote sensing systems are unfavorable. Since not all Earth Engine's users are programmers by training, there are resources like the Developer Guides page, Developers Forum, script examples, and the GIS Stack Exchange. Each of these provide either a platform for users to ask questions and be answered by others, or to get guidance on how to code common problems. Earth Engine is free for research, education, nonprofit use, and commercial evaluation, though no products generated with Earth Engine can be sold. Google doesn't currently have fixed prices on commercial licenses, so contact them directly if you have questions on how one would be acquired. Finally, App Engine can be used to create geospatial applications that can be used by anyone, even users without an Earth Engine account. Using this would help increase transparency in studies performed in Earth Engine and make your work more widely available throughout your organization. What I have shown here today is examples of how new developments in remote sensing data and processing platforms could be used to improve modeling of fate and exposure of pesticides. With Earth Engine, characterizing agricultural landscapes with greater spatial, spectral, and temporal resolution requires lower effort and cost than previously required. It also increases the ability to share across an organization or group of stakeholders through App Engine. The expansive data and efficient functionality available in Earth Engine allow for easier access to the latest satellite and modern image processing methods, which in turn support exposure modeling and environmental characterization. The outcomes can provide timely and highly relevant information to support landscape-scale pesticide investigations, whether for research, scenario context setting, or regulatory needs. Thank you for your attention and time.